Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course. Problem number 3. Alright, this is going to be a bit more difficult than the previous two, but we're going to tackle it the same. Okay, so starting out with the mass spec data, we have the molecular mass with the lowest mass isotopes being here at 194. And let's see, this, we know that this has either 0 or an even number of nitrogens then, based on this even number. The M+1 peak at 195 has a relative abundance of 6.7%. If we take that value again and divide it by 1.1%, we get the number of carbon atoms. So this gives us 6.1. So we know that there are 6 or 7 carbon atoms. Then if we look at the M+2 peak, we have 98%. So that's close to 100%. And so what that means is that bromine is present, Br. If it were greater than 100%, then we would have chlorine and or sulfur also present. But because it's just shy of 100, we know that there's a bromine. So let's just assume then that we have 6 carbon atoms and a bromine. So taking the 194 molecular mass, we have 194 minus 6 times 12, or 72, minus the bromine molecular weight that we're going to use, 79, which leaves us 43 AMU to dish out to oxygen, nitrogen, and hydrogen. Now the IR spectra shows a broad peak attributed to a possible OH stretching mode as well as a very strong carbonyl peak, and so we can guess that we might have a carboxyl group there. So that would mean that our formula has at least 2 oxygens. Now only one formula then would be possible with this, with 6 carbons, 1 bromine, 2 oxygens, and the rest hydrogens. So this is the molecular formula that we're going to be using. If you're going to go through this like in the previous 2 problems and try out with 7 carbons instead, we will find that with the requirement of having a bromine and 2 oxygen atoms, this would not be possible, and so we know that we have to have 6 carbons. So given our molecular formula here, we can then calculate the degrees of unsaturation. Again, you can see that formula under the solving of problem 1, but we can calculate this to be just 1. So this means that we have 1 ring or 1 double bond. So now if we look at the IR spectra, we see in this initial region that we always start with around 3,000 wave numbers. This broadness makes it difficult to determine for sure if the molecule contains an amine or an amide, so an NH stretch or an alcohol, but we know that there is no alkyne present. We know that also from the degrees of unsaturation that we have, that wouldn't be possible anyway. Again, because of this broad peak, it's tough to tell with certainty if the compound has alkyl or aryl or vinyl CH bonds, or if it's an aldehyde because of this broadening. But because these peaks seem to be just shy of 3,000 wave numbers, we're going to err on the side of caution and say that these could be due to simply alkyl CH stretching. So here we know that we have the broad OH. We know already from this very prominent peak that we have the C double bond O carbonyl group stretch. Now we know that we don't have enough oxygens here to have both a ketone or an aldehyde and a carboxylic acid. So likely we just have that, the COOH group, functional group in this molecule. Unlike the previous problems, we don't see the overtones in this region where I'm indicating by my cursor, or the benzene stretches around 1500, 1600 wave numbers, and also based on the degree of unsaturation, we don't have a benzene ring. With this degree of unsaturation, we can say that this single one is probably due to the carbon yield, the double bond in the carboxylic group, though. Now again, I don't have them up here, but for solving these problems, you should be using the correlation tables in your textbook. Now let's look at the Nmr data. So at 11.5 ppm, we have a broad singlet with integral of 1, so that means that we have 1 hydrogen, and this is very likely due, based on its chemical shift, to the hydrogen in the COOH, or that carboxyl group. At 2.5 ppm, we have a triplet with an integral 2. So 2 means that we have 2 hydrogen. And now, because it's a bit more complicated now, a bit more intricate, I'm going to write out all the possibilities for each of these. It would help for you to write them down separately, because I'll have to erase them to make more room. But very likely this is due to, as we've seen before, the hydrogens in a CH2. The 1.5 ppm chemical shift peak, we have an integral of 3, so that means 3 hydrogen. The most likely cause of that is part of a methyl group. And then following that up at 1.3 ppm and at 1 ppm, we have peaks with an integral of 2 and 3 respectively. So what that likely means is another CH2 group and another CH3 or terminal methyl group. So if we take this part, we can add them all up. We have 3, 2, 3, 2, and 1 hydrogens, all the way adding up to 11. So that matches our molecular formula that we described. So now, to really tell what the actual structure of this compound is, we're going to have to go into more detail of the true possibilities of these different species or different pieces of the molecule based on the splitting pattern. So let's start out with this peak. So based on the splitting pattern, the triplet here, this peak at the 2.5 chemical shift ppm could be due to these 4 possibilities or implications. As I mentioned, it could be due to the CH2 group. In one of the first 2 possibilities, for example, it would be due to these 2 hydrogens or these 2 hydrogens. And so I'm getting this implication or this information from the splitting pattern. Or it could be due to 2 identical hydrogens. In this third case, it would be referring to these hydrogens or these hydrogens. So go ahead and write these down, and then we'll move on to the other possibilities. And then we'll try to piece things together and figure out what's the most likely structure. Now moving on to this second one, the 1.5 ppm peak. So this is a singlet integral of 3. So remember, this is 3 hydrogen atoms. There's only 2 possibilities here. Like I mentioned before, part of a terminal methyl group for these 3 carbons, or it would be 3 separate CHs. It's a singlet, so no splitting, no coupling. We'll go ahead and say that this is probably not it, and this is due to a terminal methyl group. Looking at the next one, at 1.3 ppm, we have a sextet. So given here are 4 different structural possibilities for looking at the hydrogens that are underlined here, 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 and here, that could give rise to this signal with this splitting pattern. And so go ahead and write these down as well, but the most likely scenario, based on the limited number of carbons that we have, and the fact that we have to also include bromine, the carboxylic group, and that we have only 1 degree of unsaturation, this top one is probably going to be it. Finally, looking at the last one, at 1 ppm, we have this triplet with integral of 3. So again, this is 3 hydrogen atoms. And so again, I have listed out here the 3 different possibilities that would give us this triplet splitting structure. And simply due, again, to the number of possible carbons that we have in this compound, it's not going to be these bottom 2, because we would have to have 3 times this many of essentially functional groups in the molecule, and there's simply not enough carbons. And so this is what we're looking at. So then let's go ahead and take all the information that we have based on the NMR splitting patterns, the functional groups that we've identified, and tried to piece them together. So we know that we have a carboxylic group. We know that we have a bromine. From the NMR signal at 2.5 ppm, the most likely culprit is that it's due to the hydrogen atoms in a CH2, which would give a triplet splitting pattern that looks like this. From the HNMR signal at 1.5 ppm, likely have CH3. From the 1.3 ppm peak in the NMR spectrum, the splitting pattern is most likely due to the hydrogens in this position being adjacent to 3 hydrogens attached to one adjacent carbon and 2 to the other. And then lastly, looking at the peak at 1 ppm, our triplet with integral of 3, that can be attributed to the 3 hydrogens on another terminal methyl group next to a CH2. So we know that we have only one coupled CH3 group, and so that means that this guy and this guy have to be the same piece. Now I say coupled because this CH3 is a singlet, whereas the other one is a triplet. And the only other way to include this other CH2 group is to make it part of that propyl group. So then we can recombine our pieces of the puzzle here for this molecular structure. But one thing that we have to look out for now is that if you count the number of carbons, we have 1, 2, 3, 4, 5 carbons, but there should be 6 in the molecule. What that means is that we have one additional carbon that didn't show up from the proton NMR spectra because it has no hydrogens attached to it. Now, given these pieces, the fact that this carbon can't have any hydrogens bound to it, these can only be assembled in one possible way that maintains the splitting pattern that we observed in the HNMR spectrum, and that is shown here.